Hello everybody and welcome to my 25th video. This is on binary implemented quaternary logic circuits. I'll be going through the functions for the previous 3 videos which contain various quaternary algebras. Right, so I just want to go through quickly some of the design considerations for the functions I'm going to build. So these are voltage mode circuits, and consideration number 1, the output voltage must remain constant and predictable even if the input voltage varies within specified limits. Right, so the advantages of this are A, any noise on the inputs will not appear on the output, and B, if the output voltage is predictable with no loading, then the fan out can be calculated and it is easy to fault find. Fan out is the number of outputs you can connect to a single input. Number of inputs you can connect to a single output. Number 2, as a consequence of this one, voltage comparison is required on the inputs. This makes the design of the function binary. The advantages: it is straightforward to design and implement the necessary binary logic for a particular envelope function. Right. Number 3, Schmitt triggers are used for voltage comparison instead of comparators. Advantages: no reference voltages are required, although level shifting is required. This is because the Schmitt trigger hysteresis levels, trigger levels, are fixed. The noise margin is increased, and there will be no jitter on the output if the input is noisy. Number 4, resistors and sometimes diodes are used to convert the binary outputs into an NVL output. Advantages: A, the output voltage with no load is predictable and constant. If no diodes are used in the output resistor network, then the output impedance is fixed. As a significant amount of current only flows in the output resistors when the output voltage logic state is not R-1 or 0. And D, the resistance to current flow on the output resistor network is greater than the output impedance if no diodes are used. Disadvantages: if diodes are used on the output resistor network, then the output impedance varies depending on the output logic state. Right. So this is the input voltage detector encoding. We have a 74ACT14, which is a hex Schmitt trigger, and these are the voltages of logic 1 undefined and logic 0. Logic 0 is from 0 to 0.8 volts and logic 1 is from 2 to 5 volts. So for input A1, I've level shifted the 74ACT14 down 0.7 of a volt, so that 0.8 becomes 0.1 and that 2 becomes 1.3 volts. For A2, I've shifted it up 1 volt, so that 0.8 becomes 1 volt, 1.8 volts, and that 2 volts becomes 3 volts. And logic 1 is anything between 3 and 5 and 1 and 8, 0 and 1.8. So for A1, it's anything between 0 and 0.1 volts, and logic 1 is 1.3 to 5 volts. For A3, I've shifted it up 2.8 volts, so logic 0 is anything from 0 to 3.6 volts, and logic 1 is 4.8 to 5 volts for input A3. So when you combine all these together, you get the multiple valued logic state. So a logic 3 is when A1, A2 and A3 are all logic 1s, and that is 4.8 to 5 volts. A logic 2 is when A1 and A2 are logic 1s, so that's 3 to 3.6 volts. Logic 1 is when A1 is a logic 1 and A2 and A3 are zeros, so that's 1.3 to 1.8 volts, 1.3 to 1.8 volts. And the logic 0 is when all the inputs are logic 0, and that's 0 to 0.1 volts. Undefined voltage regions are in between the logic states, as shown here and here. Right, so for a logic 3, there's only about 0.2 volts of voltage range in the logic 3, and 0.1 voltage range for logic 0, which is a little bit naughty, but these maximum undefined regions are the maximum, and in practice they're less than that, so it's a little bit naughty, but you can get away with it, it still works. Right. This is the circuit diagram for A1, A2 and A3 as described in the logic diagrams, voltage range diagrams. So this is A1, which is shifted down 0.7 of a volt. This is A2, which is shifted up 0.1 of a volt, 1 volt. There's a Schottky diode there to give 0.7 plus 0.3, which is 1 volt. And A3 shifted volt down 2.8 volts. These three silicon diodes give 0.7 volts each, and the base emitter voltage there is 0.7 volts. So that gives a total of 2.8 volts, and that's A3. This is the Schmidt trigger shown in the previous logic diagram state. So as we see here, if A is a quaternary logic 0, A1, A2, A3 are zeros. A is a quaternary logic 1, A3, A2 and A1 are 1. A3 is a 0, A2 is a 0 and A1 is a 1. If A is a 2, A3 is a 0, A2 is a 1, and A2 is a 1 and A1 is a 1. And if A is a 3, A3 is a 1, A2 is a 1 and A1 is a 1. So AN, like A1, 2 and 3, equals a 1 if and only if A is greater or equal to N and 0 otherwise. So this describes the functions A1, A2 and A3. Right. So this is the output diode resistor network encoding. There are several circuits I'm going to describe. So this is circuit A. These are 300 ohm resistors. I didn't have a symbol for the ohm symbol, so I put R. R stands for ohms. These are all 300 ohms resistors, and these are the logic F1, F2 and F3 are the inputs to the outputs from the 7/4 ACT or AC logic. So this is input A, resistor network A. So F equals 0, 1, 2, 3 there, this is F. So F1 is 0, 1, 1, F2 is 0, 0, 1, 1, and F3 is 0, 0, 0, 1. So if F is a 0, F2, F3 and F1 are zeros, F1 is a 1, F3 is a 0, F2 is a 0, and F1 is a 1. F is a 2, F3 is a 0, F2 is a 1, and F1 is a 1. F is a 3, F3 and F2 and F1 are all 1s. So these are the binary outputs from the 7/4 ACT logic, and these are the quaternary outputs. So for diode resistor network B, I'm using diodes in series with resistors. This would normally be 2R, 4R and 6R But because I'm using Schottky diodes, I have to take into account the voltage drop. So that is why these resistors are slightly altered in value. So this is a 680 ohm resistor, this is a 200 ohm resistor, and this is a 390 ohm resistor. So as F is a 0, quaternary logic 0, F1 can be is a 0, and F3 and F2 can either be 0s or 1s. That's because the diode, if it's a 0, is reverse biased. If it's a 1 on F3, it's reverse biased. If it's a 1 on F2, it's reverse biased, so that just leaves F1 at 0. So for 1, F3 is a 0, F2 is a 0, and F1 is a 1. For a quaternary logic 2, F3 is 0, F2 is a 1, F1 is a 1. And quaternary logic 3, F3 is a 1, F2 is a 1, and F1 is a 1. For diode resistor network C, again 390 ohm resistor, 200 ohm resistor, and 680 ohm resistor. Schottky diodes in series with F2 and F1, these resistors. C, so this is F, these are the inputs, F1 and 2 and 3. These are the quaternary outputs, These are the binary inputs. So you can see there for logic 3, F3 is a 1, then F2 and F1 can be don't care states, either a 0 or a 1. So it doesn't matter if these are 0s or 1s, because if it's a 0, it's reverse biased and no current flows through that resistor. Same with F1, if it's a 0, that diode's reverse biased and no current flows through that resistor. So F3 is a 1 and you get a quaternary logic 3. For F is a 0, F3 and F2 and F1 are 0s, F1 is a 1, F3 is a 0, F2 is a 0 and F1 is a 1. And if F is a quaternary logic 2, F3 is a 0, F2 is a 1 and F1 is a 1. Right, for resistor diode network D, here we have 300 ohm resistors, output F, inputs F3, F2, F1. So F is 0, F2 is a 0, and it doesn't matter if F3 is a 0 or a 1, because that die is reverse biased. It's a 1, F2 is a 0, F1 is a 1, which provides current, and current flows through this resistor down there, but it also current flows through this resistor and through there. So F3 is reverse biased. It doesn't matter if F3 is a 0 or 1. For quaternary logic 2, F2 is a 1 and F3 is a 0. So current flows through that resistor and through that resistor, but it doesn't matter if F1 is a 1 or a 0, because that's reverse biased. Right, and if F is a 3, F1 is a 1, F3 is a 1, and it doesn't matter if F1 is a 0 or 1, because it's reverse biased. For logic sake 2, F2 is a 1, F1 doesn't matter if it's 0 or 1, because current flows through those resistors and down through this resistor. Right, that took a bit of explaining. I hope it makes sense. Right, so binary to quaternary conversion. This is diode resistor network E. This is F2 and F1 are there, the binary inputs. F is the quaternary output, and F2 and F1 is 0, F equals 0. So F2 and F1 equal, F2 equals 0, F1 equals 1. F equals quaternary logic 1. So F2 is a 1 and F1 is a 0. F is a quaternary logic 2. And if F2 is a 1 and F1 is a 1, F is a quaternary logic 3. So these are the inputs to the ACT gates, and this is the output. So this is straight binary to quaternary conversion. So here I have quaternary to binary conversion. So these are 74IC214 Schmitt triggers. These are transistors. These are diodes, Schottky diode, silicon diodes. And the first thing to notice is that no current flows through this current branch here. These inputs are tied together with the base of the PNP and the NPN transistors, so no current flows through there. The transistors are biased off. So current flows, if this is a 1, the output is a 1, current flows through the resistor and down through this resistor. If this gate is a 0, current flows through this resistor and down this resistor to earth. Through that resistor to earth. So if A is a 0, A2 and A1 are zeros. 0, that's a 0, that's a 1, and that will be a logic 0, binary logic 0. So that A1 is a 0, and that is a 0 also. If A is a quaternary logic 1, this moves to a quaternary logic 1. This input A2 is a 0, sorry, a 1, and this input moves from a 0 to a 1. So this turns from a 0, I1 turns from a 0 to a 1. If it's a 2, this transistor goes, this gate goes to logic 0, which acts as a pull down resistor here. So current flows through this resistor to 0, and this is a binary logic 0. So A1 is a 0. And A2 is a 1, and when A moves to a quaternary logic 3, this is a 1. This input moves from a binary logic 0 to a binary logic 1, and this A2 goes to a 1. Of course, A2 remains at 1. So I hope that all made sense. It's a bit difficult to describe, but I hope it made sense. Right. This is an alternative circuit using A1, A2 and A3. So here we have the inputs. A2 is as before, 0, 0, 1, 1 in response to 0, 1, 2, 3. So this is the a 3-input exclusive OR function, and I'm using the inputs here which are inverted to the exclusive OR function. So if you invert the inputs to an exclusive OR function, it performs the same operation as if they were not uncomplemented. So I can get away with using 1 Schmitt trigger per input instead of 2. Basically, the output from this combination is a 1 if you get an odd number of inputs to the exclusive OR function, and a 0 if there's an even number of zeros to the exclusive OR function. So For a 0, you have 1, 0, 1, which gives 0 there. For a 1, you have, what would it be? I knew I should have wrote it down. Well, you get 0, 1, 1, 0, 1, which is a 0, a 1. A2 is a 1. For logic 2, you get, what would that be? That'd be a 1, that would be a 0, and that would be a 1, so that's a 0. 3 is a 1, 1, 1, that would be a 0, that would be a 1, and that would be a 1, so that's 1. Right. So if you're going to produce and build and test these circuits, you need a signal generator and clock. So this is a 5 MHz TTL oscillator feeding to a clock, 2 74ACT 74s. These are D flip-flops, and this is the least significant crumb. The only thing I can say to find out about a quaternary digit is it's sometimes called a crumb. So crumb is 2 binary bits, so that's probably a Y. So anyway, this produces the quaternary outputs, and these are the clocks, and this is the clock to the next stage. So you basically daisy chain these stages together. These are just ripple counters, 2-bit ripple counters, so you end up with ripple counters all the way through. So I'm going to look at 2 valued unary operators. Part 1. This is part 1. This is for the algebra of my video called Quaternary Algebra, Quaternary post algebra with Karnaugh maps. Sorry. So this is A3, circuit A, which gives a 3 when A is 0 and 0 otherwise. Circuit B, this gives a 2 when A is 0 and 0 otherwise. This just knocks this voltage resistor divider network, knocks the voltage down to a quaternary logic 2. And C, this is a 1 when A is 0 and a 0 otherwise. So this resistor network knocks it down to a quaternary logic 1. So here we have a 4-valued function, the successor function. So A there, and A plus, the successor function is A plus 1 modulo 4. These are the codings for A, A1, A2 and A3 as described, and I'm using resistor network output B, output diode resistor network B, and this is the coding for this output here. So for a 1 is a 0, 1, 1, 0, 1, 1. For A plus 3, A plus 2 and A plus 1. And a 1 is a 0, 1, 1, 0, 1, 1. 2 is a 0, 0, 1, 0, 1, 1, sorry, 0, 1, 1. 3 is a 1, 1, 1, 3 is a 1, 1. A 0 is an XX0, 0 is an XX0. So this, you can use it to say that A plus 3 is A2, A plus 2 is A1, and A plus 1 is not A3. So this is the circuit diagram for the successor function. This is the diode resistor network B, and these are the A1, A2 and A3 outputs. So here we have a 200 ohm resistor, 680 ohm resistor and 390 ohm resistor. These are Schottky diodes. These are the inputs of A1, A2, A3. And this is the output. That's the input. Right. This is the double successor function, which is A plus 2 modulo 4. These are the inputs, this is the output. A3, A2 and A1 as before, coded for A. So I'm using diode resistor, input diode resistor, output network D. This is the coding for D. So this is the coding for the output. So for a 2 is a 0, 1x, 2 is a 0, 1x, 3 is a 1, 1x, 1, 1x, 0 is an x, 0, 0, 0 is an x, 0, 0, 1 is an x, 0, 1, 1 is an x, 0, 1. So this is equal to A1, this is equal to not A2, and this is equal to A3. So, right. So this is a circuit diagram. This is a A1, not A2, and A3 going and feeding into this diode resistor network. These are the inputs, this is the output, this is the input. Right. Here we have the predecessor function. This is A plus 3 modulo 4. Adding 3 is the same as minusing 1 modulo 4, so that's why the minus is there. So these are the inputs for A. These are the outputs for A minus 3, 2, 1. So I'm using resistor, diode resistor network C for it. This is the coding for F, F1, F2, F3 for this resistor network. So for an output, 3 is a 1xx, 3 is a 1xx there. 0, 0 is a 0, 0, 0, 0, 0, 0. 1 is a 0, 0, 1, 1 is a 0, 0, 1. And a 2 is a 0, 1, 1, 2 is a 0, 1, 1. So A minus 3 is not A1. This is equal to A3, not A minus 2. A minus 1 is equal to A2. So this is the circuit diagram for the predecessor function. This is not A1, this is A2 and this is A3. This is the diode resistor network C. These are Schottky diodes, 390 ohm, 680 ohm and 200 ohm resistors. These are PNP, NPN resistors. These are silicon diodes, that's a Schottky diode. These are 300 ohm and 560 ohm resistors. Right, so this is A minus is the output and A is the input. So this is the diametrical inverter function. I'm using resistor network A for this. These are 300 ohm resistors. This is the coding for A. This is a diametrical inverter, so this basically reverses the order of A in the output of the truth table. So in response to 0, 1, 2, 3, you get 3, 2, 1, 0. This is the coding for A, and this is the coding for A3, A2 and A1. So in response to 3 is a 1, 1, 1, 3 is a 1, 1, 1. 2 is a 0, 1, 1, 2 is a 0, 1, 1, a 1 is a 0, 0, 1, 1, 0, 0, 1, 0 is a 0, 0, 0, 0 is a 0, 0, 0. So this is equivalent to not A1, this is not A2 and this is not A3. So this is the circuit diagram for the diametrical inverter circuit. Here we have the 300 ohm resistors network, resistor network A. This is not A1, this is not A2, this is not A3. This is the input, this is the output, not A. And these are 500 ohm resistors and 300 ohm resistors. This is silicon diodes 1N4148, and that's a BAT43 Schottky diode. These NPN resistors are BF199s, and this NPN resistor is a BF450. Right. Right, these are the unary operators for my video called Quaternary Algebra with Karnaugh maps. These are two-valued operators which contain, for an input, quaternary input 0, 1, 2, 3, you only get either a 3 or a 0 on the output, so they're two-valued. So A0, 0 is a 3, 1, A equals 0 and a 0 otherwise, and this is this input D here. For this A11 is a 1, when a 3 when A is a 1 and a 0 otherwise. So this is a circuit diagram. This is A2 and this is A1, not A1, not A2. Yeah, and basically the output to the exclusive OR gate is a 1 when these are different, 0, 1 or 1, 0, and 0 when they're the same, either a 0, 0 or a 1, 1. So that's how you produce the output. So this output is 0 is a 0 volts, and a 5 is 5 volts for these outputs, and a 5 volts is a logic 3, and a 0 volts is a logic 0, a quaternary logic 3 and a quaternary logic 0. Yeah. Right. This is A22 F. So A22 is a 3, quaternary logic 3 when A is a 2 and a 0 otherwise. So this is A2 and output A3. And again, exclusive OR gate is a 1 when these are different, and a 0 when they're the same. So this is A33, yeah, A22. Inputs there, A, output there. For A33 A33 is a 3 when A is a 3 and a 0 otherwise. So that's just basically input A3 there and output there, input there. Nice. So for circuit H, A01 is a 1 when A equals 0 and a 1 and 0 otherwise. So this is not A2 here, output. That's not A2. For I, A is a 3, A12 is a 3 when A equals 1 or 2 and a 0 otherwise. So again, this is input not A1 and not A3, and the output is a 1 when they're different and a 0 when they're the same. For J, input to A23. A23 is a 3 when A equals 2 or 3 and a 0 otherwise. So that's basically input A2. Binary input A2, and that's the output, that's the input. K is a 0, is a 3 when A equals 0 or 2. A02 is a 3 when A equals 0 and 0, 1 or 2 and a 0 otherwise. So this is input not A3 there. Yeah, so that's the output, that's the input. And I think finally input L, A13 is a 3 when A equals 1, 2 and 3 and a 0 otherwise. So that's basically output A1. Yeah, A1. That. which is it. This is the output, and this is the input. Right. So now we have the minimal function. These are binary operators, binary meaning 2 input or more. So these, the minimum and the maximum function are common to all 3 of my algebras in my 3 previous videos. So this is the output of the function a and b, a min b. These are inputs a and b, and the output is the minimum of whatever on the inputs. Say for example 2 and 3, the minimum is 2, so it's a 2 on the input. This is the coding for a and b, as before in the unary operators. A1 is a 1 when a is greater or equal to 1. A2 is a 2, is a 1 when a is greater or equal to 2. A3 is a 1 when a is greater or equal to 3. So that's the same coding for B as for A. Same coding for the outputs, exactly the same. You take the output and you apply the same coding. So A and B, A min B3 is A3 and B3. A min B2 is A2 and B2. And A min B1 is A1 and B1, as in shown here. So I'm going to use De Morgan's theorem, change that AND into a NOR, and these inputs are inverted now. Same here, I'm going to turn that AND into a NOR and invert the inputs, and that one I'm going to use the AND, turn it into a NOR, and use the inverted inputs A1 and B1. This is because this function would require 2 Schmidt triggers per input, and this requires only 1 per input. So I can get away with using a single chip which contains 6 Schmidt triggers. So this would require you to draw a 6-variable Karnaugh map to derive the 3 outputs there. So I haven't done that, I've just noticed the relationship between the output and the input. Right. So this is a minimal function circuit diagram. Here we have A1, A2 and A3, and B1, B2 and B3 there for inputs A and B. This is the NOR function, 74ACR2, ACTR2, and these are 300 ohm resistors using diode resistor outwork A, I think, yeah, 300 ohm resistors. That's the output, these are the inputs, A min B. So this is a maximum function, output there, A max B plus B, A max B. These are the inputs, A and B. Same coding for the inputs, same coding for the outputs, A and B. So A max B3 is A3 or B3, A max B2 is A2 or B2, A max B1 is A1 or B1. So that's written here. Again, I'm going to use change the OR function into a NAND function, and here as well, just for the same reasons, just so I can get away with using 6 Schmidt trigger inverters instead of 12. So this is the circuit diagram for the maximum function. Here we have the NAND gates, SM4ACT00. These are Schmidt trigger inverters. This is not A1, not A2, not A3 for input A, not B1, not B2, not B3 for input B. This is the output A max B. Right. Then we have the difference of function. I didn't purposely design this function, I just wondered what would happen if I used exclusive ORs instead of ANDs for minimum of function and ORs for a maximum of function. And this is the output I got. The output is the difference of whatsoever on its inputs. So for example, difference between 1 and 3 is 2, or 2 and 2 is 0, or 3 and 1, difference between 3 and 1 is 2. It's the absolute value of A minus B. So for example, 1 minus 3 is minus 2, ignore the sign 2. So I'm using the same coding as before for A and B, but this coding is different for the output. Basically you count up the number of ones in either B1, B2 or B3, and you apply that same number of ones there. So a 3 is 1, 1, 1, which is there again. 0, 0, 1 is 1, 0, 0, 0 is 0, 1, 2, 2 ones there, 2, so you just add up the number of ones. So A difference B3 is A3 exclusive OR B3, exclusive OR A difference B2 is A2 exclusive OR B2, and A difference B1 is A3 A1 exclusive OR B1, which is here. And if you complement both the inputs to an exclusive OR gate, you get the same function. So these are equivalent. And I've done that there just so I can use again 6 Schmidt triggers instead of 12, which would require. Right. So this is the difference function circuit diagram. These are exclusive OR gates 74ACX6. They're 300 ohm resistors, output resistor network A. This is the output, A difference B. And this is not A1, not A2, not A3 for input A, and not B1, not B2, not B3 for input B. These are the Schmidt triggers, 74AC214, and this is the level shifting circuit diagram. Right. So this is the ampersand function. It's a 2-input function only, and it's non-commutative, which means that x ampersand y is not the same as y ampersand x. For example, y equals 1 and x equals 0 is a 2, but y equals 0 and x equals 1 is a 1. So it matters which input is x and which input is y. So I'm using the codings for the x and y. A 0 is a 0, 0, a 1 is a 0, 1, a 2 is a 1, 0, and 3 is a 1, 1. So that's the code I'm using for this. This is repeated here. The same coding for B. When y is a 0, y2 and y1 are zeros. Y is a 1, y2 is a 0, and y1 is a 1, 4 times. When y is a 2, y2 is a 1 and y1 is a 0, 4 times. And when y is a 3, both y2 and y1 are 1s, 4 times. Same coding, like I say, for x, 2 and x1. So I'm using the same coding for the output x ampersand y. 0 is a 0, 0, 1 is a 0, 1, 2 is a 1, 1, and 3 is a 2 is a 1, 0, and 3 is a 1, 1. So the output is equal to y1 for x ampersand y2. These are the same. And for x ampersand y1, the output is equal to x1. Is the same. So x ampersand y2 is y1, and x ampersand 1 is x1. Right. So this is the circuit diagram for the ampersand function. Using binary to ternary to binary conversion here, which I showed you before. This is output not A2, this is output A1. Sorry, this would be XX, not X2, and X1 for input X, and not Y2 and Y1 for input Y. So basically I'm using the quaternary to binary to quaternary conversion here. These are the 390 ohm resistors and 200 ohm resistors. This is the output X and Y. This is the input X and input Y. It matters which one is input X and which one input is Y because of the fact that it's non-commutative. So X has to have the 390 ohm resistor there and Y has to have the 2 ohm resistor there for this circuit and that circuit. Right, I think that concludes the presentation. Just like to say I hope you've enjoyed the video. Thanks for watching. Bye.